Hi, so this is first of a series of lectures for electronics. So I'm going to chunk this one up. Normally the slide presentation is 25 slides. That's a lot to go over. So I'm going to break it up into, I think, three, maybe two chunks. We'll see as we get there. But yeah, I'm going to dive right in. Here we go. All right, so the goal of this presentation is cover some of the basic info to get you ready for other classes, because we're going to be talking about a lot of stuff. I see I have power windows on there, but it's really everything in a car. I like to kind of ask the class what they think a car runs on, and I hear gasoline, petroleum, diesel, dead dinosaurs, on and on and on. And all these references to petroleum. But really, the answer I'm trying to get out of the class is that cars really run on electricity. Think about it. You got a battery that's there to start the engine. Once the engine's running, sure, the engine turns the transmission, which turns the wheels and drives the car. But literally everything else in the car these days runs off of electricity. The ignition system, which you need to run the engine, the fuel pump, which is electric, which fuels the engine, the everything in the dashboard, the power windows, the ignition key that you use to start the car, everything is electric. So really what I like to get at is that cars run on electricity these days. The gasoline engine is really just the middleman between a motor that's powered by the battery that starts the gas engine, and it turns an alternator that recharges that battery. So the gas engine's kind of there as a middleman to get things going. So here's my sweet car drawing. Um, this isn't great resolution, but I kept it simple to illustrate the whole point of the thing. So in this slide, we've got an open circuit. We've got this symbol is kind of like a battery. These little lines here each represent a cell. And what we'll learn in the future is that a car battery is actually 6 individual cells stacked up. If you've ever had anything that uses several AA's or similar type batteries, um, what we are used to calling a battery, like a AA, technically is a single cell. A battery, by definition, is a collection of electrochemical cells. So a car battery is actually 6 individual cells, and we'll learn more about that later. But what I want to illustrate here is that we got a positive and a negative. And on almost all cars, 99.9999% of cars out there, the negative post is connected to the ground of the car. This is the sweet frame of this car. All right. So the negative goes to the ground, and we need to complete a circuit to make anything work. So we run a positive wire from the battery or the alternator to whatever our load is. In this case, this is a symbol for a light bulb. And we have a switch here on the positive side. And when we connect that switch, current will flow from the positive side through the light bulb to the frame or chassis of the vehicle, completing the circuit and making the light work. A couple of things that we have on here, I'll cover them really quick. I talked about the battery already. This fun little squiggle here is a fuse. That's the symbol for a fuse. We've got a wire. These little dots here on the wire, those indicate typical connections on most wiring diagrams. Some wiring diagrams are a little different, but I'm going to keep this one simple. This little arrow that's running off into nowhere is a switch. You think of switches kind of like looking down on a gate from a bird's eye view. This one is open. This opened the circuit. Why electrical current would flow along the fence in this case, if you're making this whole thing a perimeter right here. This circuit is open because this particular gate is open. When we turn the switch on, we're technically closing the circuit. So the circuit being closed allows electrical current to flow through it. So we've got a switch there, we've got a light bulb. Hey, what's that? And we've got a ground here. This little symbol represents ground. We can, oh, I don't have, oh, I do. Haha, I have the power to erase on here. So let me draw a real quick doo-doo. Wait, oh, it scrolled. Oh man, this is out of control. Okay, forget I did all that. But there's another symbol for a ground that's common in Europe, but I'm having a little bit of trouble. Can I draw now? Oh, I can. All right, so this symbol right here, this is a little messed up. This is a messed up rake. But in European wiring diagrams, you'll see this weird rake. And this is representative of Earth, aka ground. So in the US, the typical convention is this weird upside down Christmas tree or pyramid. And in Europe, they usually use this bent up E for Earth. And you'll see that all over the place. Now, how do I make this go away? This is fun. You're learning with me, but I don't, you'll be fine. You'll be just fine. Okay, so we have a typical open circuit here. We got a battery, power source, fuse, switch that's open, light bulb that's not doing anything right now. So what do? Boom, we close that switch. Now we energize our circuit, current is flowing. We've got negative potential on the frame of the vehicle. We got positive voltage here, and current is allowed to flow through our light bulb, illuminating it, and boom, here we go. So on the slide here, I say red is source voltage, blue is ground potential. So really this whole frame ought to be blue. But what I'm trying to illustrate here is if you have a voltmeter and you put your black probe there, and then you take your red probe, and it really doesn't matter if you put your red probe there, or there, or there, or there, or there, it doesn't matter. If you go here and here on the battery, you should have about 12 volts. We'll call it 12 volts for the sake of keeping it simple. If you keep that black probe there and move your red probe along the input of the fuse, the output of the fuse, the input of the switch, the output of the switch, up to the input of the bulb, excuse me, they should all be about 12 volts. If we take our black lead, and it really doesn't matter where we have our red lead on this point, if we take our black lead and we're on the negative post of the battery, and then we move it to this ground connection, the middle of the frame, this ground connection, some part of this switch over here, any one of these combinations for red, any one of these combinations for black on our voltmeter, and we'll see a voltage difference of 12 volts. If we have the red one right here on this switch and the black one right here on this side, the input of the switch, we should read 0 volts because there's no difference in the voltage. The voltage is the same all the way across the red. Only time the voltage is difference is between the positive side of the battery to the positive side of the bulb and the negative side of the battery to the negative side of the bulb. If I have this right here, output of the switch or input of the bulb, and I put my black negative lead or common lead on my voltmeter to the output of the bulb, I'll see a difference of 12 volts. The bulb here, in this case, is consuming all of the voltage, turning that electrical pressure or electrical energy into heat and light. Is this, I want to clear, yeah, cool. So now I'm going to open a different switch. I just opened the switch on the ground. So our battery is the same. We got a negative connected to the frame of the vehicle or the ground. We got our positive, a fuse, a switch on the positive side, a bulb, and a switch on the ground side or negative side, if you want to call it that. And that switch is open, so that interrupts the current flow. Now, if we were to take our voltmeter and check it anywhere here, here, or here, compared to anywhere on the negative or ground path of the frame, then we would have 12 volts. Even if we took apart the switch and measured the part of the switch that moves compared to the part of the switch that's supposed to touch, we'll see 12 volts. We've got voltage, but since our circuit is open, we've got no current flow. Since there's no current flow, there's no work being done, and our bulb, even though it has a positive potential, is not going to glow. So we can interrupt the circuit either on the positive and or the negative side of the circuit. It stops the current flow, and then our bulb is it will only be on if we have a complete circuit, but if we interrupt any combination of these switches, our bulb is going to stop altogether. Next slide, please. All right, so this is known as a short to ground. I don't remember why I highlighted this in red, but I think it's to kind of illustrate that current will be flowing from our battery into the frame, going through the fuse, through the switch, bypassing the bulb, and going straight to the frame. This is an extreme situation. We're thinking hypothetically that this is a perfect short to ground. This is not what we want. For one, our light bulb isn't going to light. Two, since voltage isn't being consumed by a load like a light bulb, this literally creates a short circuit, and current will flow in an uncontrolled fashion until, boom, our fuse breaks. If we have a fuse, this is exactly what we put it in our wiring system for, is to protect our battery and our wires from a short circuit. If we have a short circuit to ground from a positive wire, that creates a runaway effect of current. And just like current flowing through a light bulb will cause it to glow, if we have a short circuit, some part of our wiring harness would start to glow unless we interrupt that circuit. That's exactly what the fuse is for. The fuse is a very short duration light bulb. When it pops, it makes a flash, like an old-time camera flash. But if it's doing its job and everything's designed correctly, it'll pop, it'll interrupt the circuit, it will protect the rest of the wires. If we have a short circuit and it blows the fuse, well, you might not know it's a short circuit going on in your car. All you know is something quit working, this bulb, and you might look in the owner's manual, figure out the fuse for it, and put a new fuse in there. So you put a new fuse in, it powers up the circuit, that short is still there, boom, you end up with another blown fuse again. If this happens to you, you stopped right there. You have a definite problem that needs to get solved. The wrong thing to do is to put a bigger fuse in there. If this was a 5-amp fuse and you replace it with a 10-amp fuse and you get it to work a little bit, what you're doing is you're bypassing the safety device and you're causing some other part of your wiring harness or your switch or your battery or the frame of your car to end up being the fuse. And instead of popping like this in your fuse box, some of your wiring harness will melt down, just like that little chunk of fuse did. That's not what you want. So never, ever, ever replace a fuse with a larger size fuse than what it's supposed to be. That fuse is there to protect the wiring harness and to keep your car from catching on fire. So moving on, this is something a little bit different. Most cars have 2 headlights, right? So here's an example of a car with 2 lights on it. This is known as a parallel circuit. We've got 2 circuits here. Besides this connection that jumps over to the other side of the car, this bulb and its path to ground is the same as this bulb and its path to ground. These are identical. They're moving the same direction. They're parallel. We have our battery, we have our fuse, we have our switch. And from that switch, if we were to measure put our black lead on our test meter over on here. Let me switch to black. All right, we put our black test lead right there. And then we put our test lead here. We'll have 12 volts, right? Other side of the fuse, 12 volts. This connection going into the bulbs will have 12 volts. So we've got 12 volts feeding both of these light bulbs. If we measure here on this light bulb, we've got 12 volts. If we measure here, we have 12 volts. This is ideal. This is exactly what we want. If both of these bulbs are identical for their voltage and their amperage or power, which is wattage, which I'll talk more about in another day. If both of these bulbs are identical and they're being fed the exact same electrical pressure, then the bulbs will light up at the same brightness. And that's exactly what you want for headlights. So all of the lights on our cars are typically parallel circuits. You have fog lights on the front, you have headlights on the front, you have tail lights on the back, you have brake lights on the back. All of these are parallel circuits. So what's going on here is, say this bulb runs at 12 volts. This one does too, because they're identical. They're twinsies, okay? This bulb, say for the sake of argument, when it's running, it requires 1 amp of current. I've talked about voltage and I've talked about current a little bit. And I'll give you an analogy. Voltage is electrical pressure, just like water pressure in a garden hose. Amps is a measurement of current flow. Now, current, you can think just like a river or like a hose. A small hose can't carry a large current of water. A large hose can. The analogy between water and electricity goes very, very, very deep. Think about a small hose with really high pressure. Then think about a large hose with really low pressure. You could, even though one hose is really small, say 1/2 inch, and another hose is large, say 4 or 5 inches, if you play with the pressures, you could get about the same amount of water to flow through both of those hoses. If you had to fill up a 5-gallon bucket with water, you could do it in about the same time with a small hose and high pressure as you could with a very large hose with very low pressure. So you're doing the same amount of work at the same time. Maybe that work is filling up a bucket full of water, but you're doing the same work. Electricity follows the same analogy. You can do the same amount of work either with high voltage and low current or with low voltage and high current. When we need high current for a circuit, we have to increase the size of the wire. So very small bulbs in our car, like the light bulbs that light up our dashboard, they can get by with a really small wire because they don't need much current. Great big bulbs like our headlights need a little bit larger wire because they require more current. The starter motor that gets the gas engine running requires a huge amount of current compared to anything else. So it gets the biggest wires in the car. They're known as battery cables. Now, back to the parallel circuits here. These bulbs, I mentioned that they're twinsies, right? They run at 12 volts and they each require an amp. So flowing through this wire right here, let me change to blue. Flowing through this wire right here, we have 1 amp, and 12 volts. Flowing through, I'll just highlight right there, this wire right here, we've got, guess what, 12 volts, 1 amp. They're the same, they're twinsies. Now, since we've got 12 volts and 1 amp of current flowing through each one of the bulbs, if we go back here, right before our switch, what was the voltage on this wire? It's 12 volts, right? Now we've got 2 1 amp bulbs drawing on that wire. So how many amps are in that wire? 2 amps, all right? A parallel circuit divides the current. I've got it right here. Current is divided between the separate paths. The voltage is the same on both paths. We just have a split here, so it's going in 2 different directions. Clear this one. All right, so now we're going to talk about a series circuit really quick. So our power source is the same, 12 volts going through a fuse, through a switch, and now we've got this bulb and this bulb, both pulling on that voltage. They're twinsies again. They're the same bulbs that we had here in our parallel circuit. Notice how the parallel circuit, these 2 bulbs are a little bit brighter. And in this example, they're not quite as bright. They have kind of that soft orange glow going on. Each load on a circuit, for example, in this case, a light bulb, each load consumes voltage. If these bulbs are completely identical and they have the same amount of resistance, which resistance in the terms of an electrical circuit is resistance to current flow. Both these bulbs have the same amount of resistance. In this case, when they're fed 12 volts, they want to consume 1 amp. It takes electrical pressure or voltage to push through a resistance. And a resistance is an obstruction to current flow. We have our 12-volt battery, 12 volts through the fuse, 12 volts through the switch, 12 volts going into the first bulb. We have 0 coming out. This connection from the second bulb down to the frame is 0 volts. If we compared from right here with our the black lead on our voltmeter, and right here with the red lead on our voltmeter, we'll get 0 volts across there because electrically speaking, that's the same thing. The negative on our battery, the negative battery cable down to the frame and the connection of this light bulb down to the frame, electrically speaking, they're all the same. So our voltage pressure or difference is 0 there. If I go back up here, it's 12 volts. Each of these bulbs is the same, and they're lit up, consuming voltage and turning it into heat and light. They're the same. I've got 12 volts here, 0 volts there. If I'm dividing something equally, what am I doing to that total? I'm cutting it in half. So if I have 12 volts here, 12 divided by 2, it's going to be 6 here. This is what a series circuit does. So I've got 12 volts in. Each of these bulbs in this case are identical. They're consuming the same amount of power, amps and volts, and they're cutting that voltage in half. So the voltage is divided between the 2 loads. Now, both of these bulbs only flow a current, 1 amp of current at a time. So if I take an amp meter and I put it over this wire, I've got 1 amp of current. So here's a weird thing. This whole circuit, everywhere on the circuit is going to be the same amperage on this one. If I go here, I've got 1 amp of current. If I go between the bulbs, it's 1 amp of current. If I go on this side of the ground, it's 1 amp of current. If I go on this side, it's 1 amp of current. The whole circuit is flowing the same amount of current. That's what makes it a circuit. But since we have 2 loads, 2 equal loads on this circuit, the voltage pressure is being divided. All of the voltage must be consumed on a circuit. We start with 12 volts. We split that 12 volts between these 2 loads, and we end up with 0 down here on the ground plane. Now, something that can happen on a series circuit like this, if you've ever messed with Christmas bulb lights, if you've had one bulb in the strand go out, both of these bulbs would blank out. If we have a parallel circuit and I interrupt, either one of these switches, if I disconnect this switch right here, and we'll just pretend that that doesn't exist anymore. I've opened this switch, I've affected this one light bulb, and this one left bulb would turn off, but the other bulb would keep going just fine. So it'd be something similar if this bulb simply burnt out. Well, this bulb still has 12 volts. So this bulb would keep going, which is exactly what your headlights normally do. In this arrangement, I've got two bulbs in series. If one of the bulbs is broken, if I go like that, cut that bulb in half, breaking that filament inside that bulb, current can no longer flow through that bulb, which means this bulb gets no current at all, and both of the bulbs are effectively dead at this time. So that's something to consider with the series circuit. If any part of the circuit is interrupted, if I cut this fuse right here, both of these bulbs go out. Now, on, need to clear that. On this particular one, if I were to interrupt this fuse or interrupt that switch or interrupt the connection to my battery, that would affect both bulbs in the circuit. But if I just interrupt part of that one parallel piece or leg of that circuit, it only affects the one bulb. So that's the basics of circuits right there. All the circuits start and end with a power source, our battery or alternator, but we'll keep it simple for right now. All the voltage must be used in the circuit. So used up by the loads. If it gets used by a short, it should hopefully blow our fuse, which will protect our wires and keep them from catching on fire. Any open in a circuit stops the current flow. If we have loads like a light bulb, a motor, anything on that circuit, and we interrupt the connection to that current flow anywhere on the positive or negative side, it stops the current flow there. Fuses are there to protect the wires. Hopefully I've hammered that enough. Parallel circuits divide the current, but have the same voltage on both loads. Series circuits, this one right here, divides the voltage, but the entire circuit, frame, battery, negative, positive, fuse, switches, all have 1 amp of current on this one. We start with 12 volts. First bulb drops it to 6. Second bulb drops it from 6 to 0.